Right. Good. Welcome everyone. Thanks for joining. I believe this is the third of our fall series of science seminars from the Office of the Chief Scientist. My name is Andrew Paul. I'm a senior science advisor with the office, and I'm the host for this series of seminars through the fall. For those of us that are joining from Alberta, I'd like to acknowledge that we are on the traditional lands and gathering places for Treaty 4, 6, Treaty 6, Treaty 7, Treaty 8, and Treaty 10, and homeland of the Métis peoples. Wherever you are today, I'd ask you to acknowledge your shared relationship with the lands of the First Nations, Inuit, and Métis. In the spirit of reconciliation, I maybe would just like to share something from my own journey and understanding, and that was just recently I had the chance to read the document A Shared Journey that was written by Alberta's Indigenous Wisdom Advisory Panel, along with the previous Chief Scientist for Alberta Environment and Protected Areas, Dr. Fred Rona. I found it an exceptional piece of work that has certainly helped my understanding around what is meant by multiple ways of knowing, as well as what we mean by talking about our shared place on the land. In that tradition of gathering, these science seminars provide us an opportunity to get together, to exchange knowledge from across Alberta in an open and sharing environment. So at any point during today's presentation, if you have any questions or comments, please enter them into the chat window in Teams. And then at the end of the presentation, I'll be able to read those questions and comments in the order that they've been received, and for our presenters today to respond to and provide that discussion. Your audio and video is disabled today, and that's just to maintain call quality given the number of people participating on these presentations. So today I'm really pleased to welcome Naomi Tam and Dr. Yayne-abeba. They'll be presenting on Alberta Atmospheric Deposition Monitoring Network, the past, current, and the future, a review of selected ion concentrations from precipitation between 2011 and 2020. Naomi is an air quality specialist with Airshed Sciences with Alberta Environment and Protected Areas. She received a degree in civil engineering, environmental engineering option from the University of Alberta. And trust me, I got that correct. I confirmed that title of that degree from Naomi. That's definitely a mouthful. Naomi leads our provincial atmospheric deposition monitoring network. She provides oversight, data analysis, and reporting, including reviewing provincial concentrations and trends for selected ions from that network. Yayne is currently working as a senior atmospheric scientist at Alberta Environment and Protected Areas. She has worked in air quality and atmospheric deposition in that field for 20 years and is an alumnus of both York University, Ontario, where she earned her PhD, and the University of Alberta, where she obtained her undergraduate degree. So with that, Naomi, I will turn it over to you to start your presentation. Welcome.
Thank you, Andrew. And hi, everyone. As mentioned, my name is Naomi. And today, Yayne and I will be co-presenting on work completed as part of the Alberta Atmospheric Deposition Monitoring Program. I'll turn off my camera during the presentation, but I'll turn it back on at the end during the Q&A section. Here is today's presentations outlined. First, I will provide an overview of the provincial monitoring program, including the objective, parameters of interest, and a brief history of the program. Then I will follow up with an introduction of the sampling methods used for monitoring. The next section will be the bulk of this presentation, where we will dive into the analysis of trends and concentration of selected ions in precipitation from the long-term historical data set. We will focus on trends, station, and season variability. In the end, we'll discuss on some future work of the monitoring program and open up for questions. In Alberta, we have a provincial long-term deposition monitoring program that has about 40 years of history and can be dated back to the 1980s. At that time, there were increased awareness of concern of acid deposition potentially impacting the ecosystem. There was particularly concern for eastern part of Canada. However, there were also interests to understand and surveillance the conditions for western part of Canada, including Alberta. Hence, this monitoring network was initiated. To further understand the impacts of acid deposition, there were also a sister monitoring network that collects soil samples and started around the same time. In the 1990s, consensus were made to increase sampling collection frequency from monthly to weekly. That is basically because of the data quality. There's issues with we are concerned with the data quality. A study at that time observed that the monthly sampling frequency was leading loss to ion concentration due to the extended time of sample exposed in the field. Weekly sample collection would be a better representative of the ion concentration present in the precipitation. For the next 20 years or so, the monitoring program continued to collect samples with the main focus of wet deposition monitoring. Intermittently, there were also dry deposition monitoring in the province. However, there were no long-term data set. In 2016, when the current version of the air monitoring directive was released, it included a monitoring requirement and data quality assurance process for precipitation sampling, where the data is used to infer wet deposition. The purpose of this is to bring consistency to precipitation sample collection in Alberta and to improve data quality. By 2020, it is apparent that the provincial network is in need of some updates. To align with common scientific practices and to increase data credibility, the current Alberta stations have transitioned into joining the National Atmospheric Deposition Program, known as NADP, and the Clean Air Status and Trends Network, CASNet. Both networks are based out of the United States and are being internationally recognized. Some other jurisdiction and agency are also part of these network, includes Yayne-abeba airsheds under the OCS monitoring program, the Saskatchewan Ministry of Environment and Environment Climate Change in Canada. A phased approach was taken for the station transition in Alberta, as it involved many additional work. This include equipment upgrades and additional training for the new sampling procedures. By April of this year, I'm proud to say that all Alberta stations have successfully transitioned over. The current monitoring program objective is to measure the transfer of pollutants from the atmosphere to sensitive ecosystem within natural regions. The network collects regional representative samples that can be used to quantify deposition of pollutants that can be harmful to the ecosystem. This includes acidifying substances, base cations, and nutrient nitrogen. The parameters of interest are listed on the slide. The map shown on the right is all the sampling sites existed as part of the deposition monitoring program. And in 2024, we have 6 wet deposition stations and 1 total deposition station, meaning sampling for both wet and dry. The 7 active stations are shown as green dots on the map. Here, I would like to take a second to recognize all station operators who diligently collect the weekly samples as part of this monitoring program. They collect samples at various conditions, even on hot days and cold winter months. I'm very proud of them, and they rarely miss any sampling collections. And I see that some of the operators are called in today, and thank you for the contributions for collecting sampling. The continuous data set are very valuable to this monitoring program. This is Elk Island Station, which is located in central Alberta, about 35 kilometers east of Edmonton. The station is located within a national park and is known to be downwind of Edmonton and industrial heartland designated zone. The station is a total deposition monitoring station, which consists of a collector for a precipitation sample and a gauge for depth measurement for wet deposition. And as mentioned before, the samples are collected weekly on a weekly schedule. For dry deposition monitoring, it is collected as part of filter packs and passive filters. The filter pack is deployed at a height of 10 meters with a constant flow rate of 3 liters per minute. And the ammonia passive is deployed at a height of 2 meters. Filter pack samples are collected on a weekly schedule, while the ammonia passive samples are collected on a biweekly schedule. Once the samples are collected, they are shipped in a timely fashion to their respective lab for sample analysis. Since joining NADP and CASNet, one of the many benefits is that the Alberta data is easily accessible through their online data portal. In NADP data portal, one can download the data for precipitation ion concentrations to infer wet deposition and ammonia passive data for ammonia dry deposition. Alberta station ID will begin with AB, followed by 2 numeric digits. For example, Elk Island is AB35. In the CASNet data portal, one can download filter pack data for dry deposition. Alberta station ID will begin with ALB, followed by 3 numeric digits. The only current active station we have right now is Elk Island, which is ALB 801. Some of the 2023 data and all data moving forward will be available through the NADP and CASNet data portal. Historical data from 2013 and 2022, and soon some of the 2023 data will continue to be available while Environment Canada NatChem database. And any data prior to 2013 can be requested directly through our program mailbox, which will be shown at the end of the slide deck. The remaining of the presentation will be discussion of work completed as part of the concentration and trends report that is publicly available on Alberta OBERT government. Like many historical data set, there were data quality issues such as data gap. The full historical data set went through the standard data quality assurance process based on the government published data handling manual. And additional criteria was also considered to improve the overall quality of data set. The details of the QA/QC process are documented in the report. Based on that process, we have only considered the data from 2011 to 2020 to be included in the report and in this presentation. And we have also included only 7 stations as part of this study. In terms of data analysis, the study focused in looking at trends during the study period, variability between selected stations based on their annual concentrations, and ion concentration variability depending on seasons. In Alberta, precipitation typically falls as rain from June to August, and in its frozen form, such as snow, from December to February. Mixed precipitation, meaning rain and snow, typically can occur during fall and spring months. The amount of precipitation also vary from year to year, as it is illustrated in this figure. The black circle dots are the annual median of total precipitation depth of the 7 stations included in the study, and the gray area bounds the 25th and 75th percentile of the annual precipitation depth. And it basically illustrates the ranges between from station to station. The hollow diamond shape points associated with the secondary y-axis, indicating the median of the total number of wet samples collected for each year. As you can see, there is variability for sample volume collected throughout the study period. And basically to account for this, we have used the volume weighted concentration, and it is calculated based on the formula shown on this slide. The volume-weighted concentrations are less likely to be impacted by the total collected sample volume for any particular year. Moving on to trend analysis, the Thiosan method, which is a linear trend method, is used to estimate trends in ion concentration in precipitation. This method fits the slope by selecting the median of the volume-weighted concentration by using all pairs of samples. The bar chart basically here shows the annual volume-weighted concentrations for each year, and the line is indicating the Thiosan trend over the study period. Trends with a p-value less than 0.1 were deemed to be statistically significant, and it is denoted with the dashed line. The figure is showing the provincial trend where it incorporates data from all 7 selected stations. For the interest of time, I'll be focusing on nitrate ion, sulfate ion, and precipitation pH. Fuel combustion is one of the largest sources of nitrate, which leads to eutrophication, causing excessive nutrients accumulation and indirectly affecting wildlife through changes in the habitat. Provincially, nitrate ion concentration have decreased between 2011 to 2020, and that is statistically significant based on our analysis. This provincial trend is comparable to those observed in regions such as the Rocky North and North Central in the United States. These regions were selected for comparison because of their close proximity to Alberta. Oil and gas is one of the major sources of sulfur dioxides, which reacts with atmospheric oxidants to form sulfate and alter soil chemistry. And this impacts terrestrial and aquatic ecosystem health. Comparing the provincial trend with other literature, the statistical decreasing trend is found to be in a similar range to other studies by NADP and Environment Canada. The observed trend for nitrate and sulfate are of the decreasing trends basically is likely reflecting to the improved NO2 and SO2 emissions management by various government policies over the year. In the past, acid rain or acid precipitation is one of the main concerns for deposition monitoring. The typical range for natural precipitation would have a pH of 5.6, and a pH value lower than 4 will be considered as acid rain. Provincially, the precipitation pH is slightly above the typical range, and we are observing a slight increase from 2011 to 2020. This is kind of expected as it is in agreement with other observed trend with other ion parameters. We are aware the provincial pH trend in soil reported by a paper in 2019 is observing decreasing trend, which is not what we're observing here. But based on what we're preliminary look at other literatures, it is known that the soil chemistry can have a delayed response to changes of precipitation chemistry. And in additional, precipitation is one of the many ways that can alter soil chemistry, where there could potentially other internal soil process which is driving the soil chemistry in Alberta. Moving on to station variability, this section will be looking at the differences of ion concentration between the 7 selected stations. Some factors we have observed to cause station variability in ion concentration include anthropogenic emissions and natural sources. The land use adjacent to the monitoring station could also cause differences to concentration observed. Here are the range plot, which shows the within and between station variability for the 7 different stations. The sample median is indicated by the blue square, and the means are indicated by the red circle. The whisker is spanning the 95th percent confidence interval. Generally, the mean volume-weighted concentration of ion and precipitation pH at station classified as urban observed higher concentration than at the non-urban classified stations. For example, for urban stations, Calgary Northwest, it is situated in the largest population center, has observed one of the highest mean for nitrate, sulfate, and base cation. And for Fort McMurray Station, also an urban station, which has observed highest sulfate concentration in the program. And this might have suggested the nearby oil sands activities have contributed to this. Anthropogenic sources contributing higher iron concentration also evidence in chloride ion, and that is evidence in stations by Beaver Lodge. This station is located near a major highway between Beaver Lodge and Grand Prairie, and chloride ions is often associated with road de-icing. Agriculture activities contributing to higher ammonia concentrations are also evidence. At stations, land use basically adjacent to farmlands, and this is referring to Dixon Dam, where the volume-weighted concentration of ammonia ions are higher than other stations in Alberta. Base cations also often associated with wind-blown dust, and that is believed to be naturally occurring in Kananaskis, and as this station is observing one of the higher base cation concentration. Kananaskis is basically located within a protected area and have minimal anthropogenic sources. Other than the higher base cation, they have at this station have relatively low concentration in nitrate and ammonia ions. For the next section is the season variability, and I would like to pass it on to Yayne for this part of the presentation.
Thank you, Naomi. So in addition to what Naomi has already presented on, we also looked at seasonal variability or seasonality of ion concentration and precipitation. And we did this because we wanted to kind of evaluate what factors were affecting ion concentration and precipitation. So what factors, thanks, Naomi. So factors that could be affecting ion concentration and precipitation are similar to what Naomi already said about when she was presenting on between station variability. But precipitation is, in effect, scavenging pollutants from the atmosphere, and atmospheric deposition in general is a form of cleaning the air or cleaning the atmosphere. So whatever would affect concentrations in the atmosphere would also affect concentration and precipitation. So factors that could affect this include mixing height, and this is the height in the atmosphere above the surface of the Earth, where there's relatively good mixing due to turbulence. And this mixing height is lower in the winter times and overnight, for example, and higher in the summertime. Other factors that could be affecting the concentrations would be conditions that promote the formation of secondary pollutants. Naomi mentioned a little bit about this as well, and so there are factors such things as like temperature or relative humidity or availability of solar radiation can all affect the formation of secondary pollutants, which are pollutants formed as a result of atmospheric reaction or atmospheric chemical reaction. It was already mentioned that obviously level of emission in the area also affects the concentration, and land use and land cover in a way are associated with level of emission. Naomi gave example of Kananaskis, where they could be unvegetated areas that could lead to increased base cation concentration, and land use could be such things as application of ammonia, for example, or the presence of industry in the area. In addition to atmospheric concentration, the amount of precipitation and maybe even the type can affect concentration of ions in precipitation. And Naomi mentioned about how we have used the volume-weighted mean in order to counteract that component. Next slide, Naomi. Okay, so my task is to talk a little bit about the seasonality or seasonal variability of iron concentration and precipitation. And what you see here is the overview of the various iron concentrations over the indicated months for the period of 2011 to 2020. And the colors indicate the various stations, and obviously the x-axis indicates the months and the y-axis is the volume weighted concentration. In the next few slides, I have selected 3 of the ions to kind of go in more depth. But generally, you can see from this overview slide, there is a tendency to see seasonal variability. And for the purpose of that report that Naomi mentioned, we looked at seasonal variability more qualitatively than looking at statistical significance. Next slide, Naomi. So Naomi already mentioned that nitrate concentration in the atmosphere is formed as a result of well, it's a secondary pollutant. It's formed as a result of atmospheric chemistry that involves NO2. And what you see in the figure there is the seasonal variability or the monthly mean concentration of nitrate. It is quite evident in most of the stations. Actually, I would say in all of the stations, the concentrations are higher in the colder months, more specifically February and March, than they are in the warmer months in June, July, and August, and even September. This is even evident in stations that are relatively remote, like Kananaskis, as well as the stations that are within urban or near urban and industrial areas. This seasonal variability is consistent with what we see with nitrate concentration in particulate matter, as well as similarly with NO2 availability. So NO2 atmospheric concentration also has similar variability. And the formation of nitrate is actually promoted, obviously, by the presence of NO2, but also by lower temperatures and higher relative humidity. Next slide, Naomi. Okay, sulfate is also a secondary pollutant. It is formed as a result of atmospheric chemistry that involves SO2. And initially, you might think that the sulfate seasonality is similar to that of nitrate, but you will note that sulfate actually has peaks in the springtime and has a secondary mode in the summer. And unlike nitrate, sulfate is actually, the formation of sulfate is also promoted by the availability of solar radiation. Therefore, that would explain the summertime peak that we are seeing. And like nitrate, this seasonal variability is comparable to what we see in sulfate concentration in particulate matter. Next slide, Naomi. So this is the last slide I have for the monthly, the seasonal variability of ions, and I thought I would include it because it's very different from the ones that I've illustrated before. Well, not very different. It's quite different, but also highest in the colder months. Naomi mentioned that chloride in Alberta, because we don't have sea spray, is associated with de-icing. So we would expect to see it to be higher in urban or near urban areas. But as you can see from this figure, this seasonal variability is more evident at sites that are near road. For example, we hardly see this seasonal variability in Kananaskis, but it's quite evident in Calgary Northwest, Beaver Lodge. Now we mentioned that this station is quite near a highway, and as well as Fort McMurray. Next slide. So that kind of summarizes the seasonal variability of ion concentration in precipitation. And I would like to kind of summarize some of the things that were presented today. This is actually, the report that Naomi mentioned is a report using data from this network and there hasn't been a report from this network for quite a while. So we're very excited to look at the data and be able to release the reports using the data collected within the deposition network. Some of the things that we see is that, as would be expected, ion concentration are higher at stations near or in urban sites. And seasonal variability is present, and some of the drivers that result in this variability include meteorological conditions as well as seasonal activities like the de-icing that I just mentioned. And we did do trend analysis on all of the ions that are analyzed for within the samples collected, and what we found to be statistically significant is a decreasing trend for nitrate and sulfate, and an increasing trend for precipitation pH, meaning that precipitation was becoming less acidic. However, the observation we made in precipitation pH does not quite align with a study that looked at soil monitoring in Alberta. And Naomi already mentioned that this could be due to a lag in soil response, and this actually has been observed in other studies as well. So we will have to continue monitoring and look at the data again and see if we see more of an alignment between soil, pH, and precipitation sometime in the future. So I said the future, so next slide. What is planned for the network? We currently have 7 stations. Our newest station is Calling Lake. You see that they're right in the middle of the red area. The map in the base of that map, the base map in that figure is actually a suitability map, where the red area indicates where the best location for siting a station, and the black area indicates, areas that are not as suitable for monitoring. So during our presentation, we talked a lot about stations that are in urban areas, but we have since stopped monitoring in urban areas, and have limited the deposition monitoring to natural areas. So Calling Lake, our newest station, was placed where it is to fill a gap where we thought that there was a high need for monitoring. But you also see that from the distribution of the stations, there is a spatial gap in the northwest and a spatial gap in the southeast. And it would be nice to have monitoring deployed in those areas, so we have a relatively well spatially distributed monitoring network. And this was alluded to earlier in the report, in the presentation, but today's presentation largely has been focused on precipitation, or we also call it wet deposition, but atmospheric deposition includes both wet and dry deposition. And we currently just have only one station, Elk Island, where we have dry deposition included. And it would be really beneficial to include dry deposition in additional sites. And next slide. Okay, so Naomi already mentioned the operators of the station that do the collecting through many various seasons. We also have staff from within Alberta Environment and Protected Areas that are not presenting today, that are an integral part of this network. That includes Ramnik Sanhu from the Air Monitoring Group and Courtney Stanley from the Airshed Sciences, that also deserved acknowledgement of their effort to support this network. Next slide, Naomi. Okay, I think now we handed that back to Andrew because we've... Oh, I should point out that Naomi mentioned the mailbox for the deposition monitoring program, and that is noted here as well.
Thank you so much, Yayne and Naomi. Great presentation. A lot of interesting stuff there. I'm an aquatic person, but I always love to hear your presentations on the air side. Before we do close, I just want to remind everyone that our next presentation is going to be on Tuesday, November 5th. That's going to be Dr. Celeste Barnes from the University of Lethbridge, who will be presenting on mapping watershed snow water equivalent from LIDAR, snow depth, and field snow sample density models. If you're not on the mailing list for these seminars, please send an email to the Office of the Chief Scientists, which I will get right this time. It's epa.ocs, and that's at gov.ab.ca. And with that, again, I would like to thank you both, Naomi and Yayne, for a great presentation today. Thanks for sharing that work, and thank you everyone who joined in today and provided the great discussion. Thanks, everyone.